Okay, we're going to continue on now with pedigree analysis. So pedigrees are used to analyze natural populations that typically result from uncontrolled crosses. So humans is a very common example of this. You can't really control how humans breed with each other, like we can with pea plants, and so we have to come up with some sort of technique to describe the relationships between relatives, so we can do some sort of genetic analysis. So pedigrees are a family tree with respect to a given trait, and we're going to continue this work kind of under the idea that there's a single character under analysis. And typically this is a disease because for humans we're very interested in obviously medical issues. So the trait, in this case, two traits are either having the disease or not having the disease. And so the analysis of this pedigree allows us to determine information about the inheritance of the disease and then predict the phenotype and genotype really of individuals. And so this can be both dominant and recessive diseases. So the relationship between the alleles can go both ways. A disease can be dominant or it can be recessive. And this can actually be determined from analysis of the pedigrees. So just some basics. So a circle indicates a female, a square indicates a male, and typically we're interested in the people affected with the disease, and so if someone is affected with the disease, they are colored. The circle or square is colored in, so this indicates that they have the disease. If two individuals have a baby together, then that's indicated by a single line. So these are the parents of the individual, one female and one male, biological parents. You can also have situation where consanguineous parents have a child, and that occurs when there is a relationship between the two parents, a familial relationship such as cousins, first cousins, second cousins. This is important for recessive diseases because these diseases are typically very rare, but in these sorts of cases, the presence of this disease can become much more common. And then when you look at the offspring, each sets of parents can have multiple offspring, and they are typically numbered in birth order. So in this case, there was a male child that was the firstborn, a female child, and then a male child. So there was four full siblings indicated. You can also have twins, which are either fraternal, dizygotic twins, which have different genetic, different genotypes, or can have different genotypes, or you can have identical twins. In this case, the sex must be the same, and then the genotypes of those twins should be identical to each other. And then you can also kind of summarize if you want to we won't see this really in the class, but you can also summarize a large number of unaffected offspring by simply indicating a number inside the square or the circle for how many individuals. Proband. The proband is indicated by a capital P, and the proband is the first individual in a family that is studied for the disease. So typically what might happen is that an individual sees a doctor, the doctor diagnoses the disease as some sort of brand new genetic disease, or maybe the first member of the family to have a known genetic disease, and then from there they decide to do analysis of the inheritance of this disease in the entire family. So that first individual that is seen with this disease is called a proband. If a person dies, that's indicated by a line, so that's how you know whether the person is currently alive or dead. And then if you want to, you can indicate carriers for a disease, so this would be for a recessive disease by a dot in the center. And then you also indicate generations. This allows you to name and identify individuals using Roman numerals. So there's a lot of rare genetic diseases, so rare in the sense of how many people in the population have it, and these can be traits or diseases that lead to death. and some representative, recessive, and dominant human traits are kind of listed in this table from your textbook. Cystic fibrosis, it's a really bad disease to have. Color blindness, most people can live a pretty normal life with color blindness. So these are two examples of recessive diseases. They can also be dominant traits. Huntington's disease is kind of one of the most common dominant diseases that is studied in general. So here's an example of two pedigrees, two families. In the first case, we see a pedigree from an autosomal recessive trait. In the second case, we see a pedigree from an autosomal dominant trait. So what do we mean by this? So kind of following the so the individuals that have the disease in this case are little a, because this is an autosomal recessive trait. So if you're homozygous, then you have the disease. If you're not homozygous, if you're heterozygous for either big A or big A, then you're normal. And then in the second case, the dominant trait, either this homozygous or the heterozygote would have the trait. And typically, if you have the disease, because most diseases are very rare in the population, typically if you have an autosomal dominant disease, you're actually a heterozygote. It's very rare to have the double homozygous, although it is possible. So we look over these pedigrees, and one of the first things I mentioned is the fact that one of the first things you might be interested in studying for a disease is whether or not it's a recessive disease or a dominant disease. And so how do you do that? So one indication is that recessive traits typically skip generations, and if they skip a generation, then you know for certainty that it has to be an autosomal recessive trait. Sorry, you know that it has to be a recessive trait. So for this individual to have the disease, we know that it must be little a. And so if this individual has to have received one of the gametes from their mother and one of the gametes from their father. And so this is impossible to have if the trait was dominant. So if the trait was dominant, there's no way you could get it from an unaffected parent. And so the reason for that is, let's say it looks something like this. And this individual was heterozygote. In this case, we know that this individual received one of the alleles from one parent and one of the alleles from the other parent. Okay, so this individual right here I'm referring to is 3-3, so named for the generation, and then this number right here, 3-3. So if this individual was dominant, carried a autosomal dominant trait, then we know it would have had to receive this big A allele from one of its two parents. So in that case, this parent also would have to have it. And so because that's impossible, then we know from looking at this pedigree that this must be an autosomal recessive trait. So that's an example of what you might do to try to analyze this. Whereas when you look at the dominant trait, we see every generation an individual has the trait in question or the disease in question. So this family, for example, neither one of the individuals have it, and so none of their offspring actually are able to have it. Whereas when you look in the third generation, any of these individuals that has it has one of the parents that have it. So what sort of analysis do we want to do beyond just determining if it's recessive or dominant? Another thing you want to do is try to predict either whether the person has the disease or whether the person can give the disease to another offspring. So what do I mean by that? So we can determine the genotype for a number of individuals on this pedigree. So we know all of these individuals that have the that have the trait must be homozygous recessive, and so we can fill in the genotype for all of these individuals. However, we now have additional information about other members of the family as well. And so how do we know that? So again, we know that this individual must have received the homozygous recessive allele from both parents. So both of these parents, 2, 3, and 2, 4, must also have a recessive allele. So what is their other? So they're diploid, so they have 2 copies of each gene. And so we also know that they cannot be homozygous recessive because they would have the trait. And so this pedigree indicates that they do not have the trait. And so we can fill in the second allele, and we know for certainty that these individuals are heterozygotes. Do we have any sort of information about these individuals? 3-1, 3-2, 3-5, and 3-6. So we know for certainty that they're not little a, but they can be both big A, or big A, little a. So this, a cross between these individuals can produce all different types of genotypes. For these particular individuals, we know that they all can potentially be either carriers, so heterozygotes are referred to as carriers, or they could be homozygous with a non-disease allele. So this individual right here, 1, 2, typically we would assume that they are not carriers for the disease unless there is other information that contradicts us. And in this particular pedigree, there is not information that contradicts us. So again, most diseases are rare, so you assume that most individuals are not carriers for a disease. So in this situation, we have pretty much certainty, again, for the genotype of all these individuals. Okay, so these are all going to be carriers of the disease. Okay, and this is just the same as this. So from this information so far, we've been able to fill in a large amount of information about this pedigree. And now we can continue doing this as well. So in this situation, normally we would say that these persons are not carriers, but now we have information that contradicts that. So this individual right here must have received the disease allele from one of his 2 parents, so we know at least one of the 2 parents is a heterozygote carrier. And so the other individual we would assume would not be a carrier, again using the assumption that most individuals are not carriers. And so under this situation, these 3 individuals we know do not have the disease, so they can't be little a, but there is an equal probability that they are either big A, or big A, little a. So this individual can be either big A, or little a, and that, big A, little a, and that is completely determined by which gamete is passed on by their father in this case. So that's part of what you want to do when you look at these pedigrees, but the other part that you want to do is also actually try to predict probabilities. So if I ask you, for example, the question, what is the probability that this individual is a carrier, right here, we can simply do this cross right here, big A, little a. And so if we did a Punnett square for that, the father could provide both big A or little a with equal probability, while the mother would provide big A with certainty, and so there would be a 50% chance that the person is a carrier and a 50% chance that the person is not a carrier. So in this situation, we would say it's a 50% chance that this person is a carrier. How about this person? What is the chance that this person 3-1 is a carrier? And so, you might just decide to answer that question by, again, doing a Punnett square, and say, sorry, this and that, and say, there is a each parent can now give either gamete, and so this is just simply a monohybrid cross, and so if you completed this Punnett square, you would have something like this, where you follow the genotype relationships that we saw in the Mendelian, where it's 1/4, 1/2, and 1/4. That's the prettiest writing ever. So you might say, okay, so what is the probability that 3-1 is a carrier? It's 1/2. That, unfortunately, would not be correct, and the reason that's not correct is because we know with certainty that this individual does not have the disease. So we know for certainty that this individual is not little a. And so what we have to do is we have to renormalize the probabilities to account for that. And so there's a 1/4 chance that they're homozygous, 1/2 chance that they're heterozygous, and if we add that up, now that equals to 3/4. And so renormalizing just means that you take the initial probability and divide it by the new total probability. So the chance that this person is a carrier is just simply 1/2 divided by 3/4, or 2/3. So this is an example of how probability becomes very important for dealing with understanding pedigrees. And so we're going to have some activities that are a bit more difficult, but kind of follow the same logic. And the logic is simply, how do you identify the individuals that you have certainty over their genotype, and then how do you identify individuals that have some sort of probability of different genotypes, and then you need to kind of renormalize to capture situations where you can exclude certain genotypes based upon their phenotypes. So just to remind you, the way we were able to exclude that these individuals were not homozygous recessive is because we knew that the person did not have the disease or the trait. Okay, so that was a lot, and that will end the section on pedigrees.